Welcome to Physical Chemistry 1 Level 3. I am Dr. Min Soo Lim, and I will show you how to carry out the lab in the experimental and theoretical aspects. You will do a 2-week-long experiment titled Hits of Ionic Reactions. I want you to follow my instruction very thoroughly, slide by slide. After you watch this online pre-lecture video, you should take an online quiz that is posted on the 12. You may play this video as many times as you want, but you have only one chance to take the quiz. Before getting started, I want to clarify the difference between ionization reactions and neutralization reactions by taking water as an example. A water molecule may ionize itself and generate a proton as a cation and hydroxide ion as an anion. It is called ionization of water. However, the formation of water from acid-base neutralization reaction takes a different route. Arrhenius describes that an acid releases a proton and a base releases a hydroxide ion. Both ions react and produce a water molecule. You will see different types of ionization reactions and neutralization reactions in the following slides. Please make sure that you are not confused by these two different types of reactions. Acid-base neutralization reactions are exothermic. It means that mixing an acid and a base raises the temperature of solution because a neutralization reaction releases heat. Hydrochloric acid reacts with sodium hydroxide and produces water and sodium chloride as reaction products. Since the reaction is exothermic, the change of reaction enthalpy, or delta H1, is negative. Let's write the full ionic equation of the reaction. Only strong electrolytes break apart into their component ions in a full ionic equation. Strong electrolytes are strong acids, strong bases, and soluble ionic compounds. Weak electrolytes are weak acids and weak bases. Non-electrolytes are the rest of molecular compounds. HCl is a strong electrolyte because it's a strong acid. NaOH is a strong electrolyte because it's a strong base. H2O is a non-electrolyte. NaCl is a strong electrolyte because it's a soluble ionic compound. In a full ionic equation, HCl and NaOH break apart into ions because they are strong electrolytes. H2O should be written as is because it's a non-electrolyte. NaCl breaks apart into ions because it's a strong electrolyte. Net ionic equation is constructed by eliminating spectator ions from both sides of the full ionic equation. Since spectator ions are not involved in a reaction, they are part of surroundings, not the system. Please be advised that net ionic equations will be used to represent chemical reactions in the upcoming slides. So, the reaction of hydrochloric acid with sodium hydroxide is represented simply by this equation. A proton reacts with a hydroxide ion to produce a water molecule. Heat that is associated with this reaction is of course delta H1. Interestingly, ionization of water is simply the reverse reaction of this acid-base neutralization. That is, water ionizes into a proton and a hydroxide ion. The heat of ionization of water is negative delta H1 as a result. You will use 2 acids and 1 base in this experiment. The 2 acids are hydrochloric acid and malonic acid. The base is sodium hydroxide. Malonic acid is a weak diprotic acid. Since it's a diprotic acid, it has 2 acidic protons that are highlighted in red in this structural formula. The malonic acid will be denoted by H2R. How can you write the equation for the first neutralization reaction of malonic acid with NaOH? Malonic acid H2R reacts with hydroxide ion to produce hydrogen malonate or HR- and the water molecule. How about the second neutralization reaction of malonic acid with NaOH? Now, the HR- reacts with another hydroxide ion and produces malonate R2- and another water molecule. Now then, how can you write the equation for the first ionization reaction of malonic acid? Malonic acid H2R breaks apart into HR- and a proton H+. How about the second ionization reaction of malonic acid? The HR- breaks apart into R2- and another proton H+. Now, do you see the difference between the neutralization reactions and ionization reactions? Neutralization is simply the reaction of an acid with a base or hydroxide ion. And ionization is simply to break a molecule into its component ions. The goal of this lab is to determine the heat of second ionization of malonic acid, which is described by the last equation. The heat associated with the reaction is represented by delta H3. Unfortunately, we cannot determine the heat of second ionization of malonic acid directly. So, we will determine it indirectly using Hess's law. Hess's law states that if a reaction is carried out in a series of steps, delta H for the overall reaction will be equal to the sum of the enthalpy changes for the individual steps. Ionization of water is described simply by reversing acid-base neutralization reaction, and the heat associated with it is negative delta H1. The second neutralization of malonic acid is written as HR- and it reacts with OH- and produces R2- and water molecule. The heat associated with the reaction is represented by delta H2. These two reactions can be combined and it would produce a new reaction, that is, HR- splits into R2- and H+. Isn't this reaction familiar with you? It's the second ionization of malonic acid. Consequently, the heat for the second ionization of malonic acid, delta H3, is equal to delta H2 minus delta H1. This combining process of reactions can be described pictorially with this energy diagram. Formation of water from acid-base neutralization may split into 2 steps. The first step is the second neutralization of malonic acid, and the second step is the reverse reaction of the second ionization of malonic acid. Therefore, the heat for the overall reaction, delta H1, is simply delta H2 minus delta H3. This equation can be written with respect to delta H3. That is, delta H3 equals delta H2 minus delta H1. As you may know by now, delta H1 is the heat of the neutralization of HCl and NaOH. And delta H2 is the heat of the second neutralization of H2R. Now, the question is how to determine both delta H1 and delta H2 experimentally. Now, I am going to show you the experimental procedure of the determination of delta H1 and delta H2. First, you have to determine the voltage and current of the heater that needs to raise the temperature of 132 milliliters of water inside a calorimeter by 0.1 Celsius in every 10 to 15 seconds. The volume of water, 132 milliliters, is the same with the volume of acid-base mixtures. The calorimeter consists of a temperature probe, heating coil that is connected to power supply, voltmeter, ammeter, and a dual flask. First, start the Logo Pro program on the computer. Open the cover of the calorimeter and add 132 milliliters of distilled water into the dual flask. Put the cover back. Please keep in mind that the heating coil must be completely submerged in water. If not, the heating coil will be burnt when the power is on. Turn on the power of the power supply. Use two knobs on the power supply to increase the temperature of water by 0.1 Celsius in every 10 to 15 seconds. Record the voltage on the voltmeter and ampere on the ammeter. Now, let me show you how to determine the molar delta H1 experimentally. Open the cover and add 120 milliliters of 0.25 molar HCl solution into the dual flask. Put the cover back and let the Logo Pro draw the baseline of the heating curve for 60 seconds. Keep agitating the apparatus to maintain thermal equilibrium inside a calorimeter. Pause the Logo Pro. Open the cover and add 12 milliliters of 2.5 molar NaOH solution into the dual flask. Put the cover back immediately. Continue the Logo Pro scanning for 300 seconds. Keep agitating the apparatus. Turn on the power of the power supply to initiate heating. Continue heating for another 300 seconds. Turn off the power of the power supply. Continue running the Logo Pro for another 300 seconds. Stop the Logo Pro and save the heating curve in text file for further data analysis. This is a generic copy of heating curve. There are two regions of temperature increase, delta T1 and delta T2. Delta T1 represents a temperature increase due to an exothermic chemical reaction. I mean a neutralization reaction of HCl and NaOH. It will be used to determine delta H1, that is, heat of neutralization of HCl and NaOH. Delta T2 is due to the intentional electrical heating, and it will be used to determine the heat capacity of calorimeter, Cp. Heat capacity is also called calorimeter constant. The first step to determine Cp is to estimate the heat that was transferred electrically into the calorimeter during the intentional heating. The heat transferred, Q, equals I times V times T. I and V are current in amps and voltage in volts. That gives rise to 0.1 Celsius increase of 132 milliliters of water in every 10 to 15 seconds. T represents the actual time spent for the intentional heating. It is approximately 300 seconds. Please keep in mind that the unit of Q is joule, which is equivalent to amps times volts times seconds. Heat capacity Cp is defined by Q over delta T2. The unit of Cp is joules per Kelvin. Now, you're ready to determine delta H1. Delta H1 equals negative Cp times delta T1. Please don't forget the negative sign because the neutralization reaction is exothermic. Since delta H's in the literature are reported in joules per mole or kilojoules per mole, you may want to convert delta H1 to molar delta H1 by dividing delta H1 by the number of moles of HCl. The HCl is the limiting reactant in this reaction. You have to go through additional step to determine delta H2 because delta H2 is the heat of second neutralization of H2R and NaOH, which is represented by the following reaction. H_- reacts with OH- and produces R2- and water. An additional step is to remove a proton from H2R by titration and generates HR-. Keep in mind that H2R may undergo two deprotonation steps because it is a diprotic acid. Removing the first proton of H2R by a hydroxide ion produces HR- and a water molecule. Removing the remaining second proton of HR- by another hydroxide ion produces R2- and another water molecule. The titration curve looks like this. It has two equivalence points. The initial acid solution contains only H2R. As titration begins, the solution has newly formed HR- and unreacted H2R until it reaches the first equivalence point. The solution contains only HR- at the first equivalence point. As titration proceeds, after the first equivalence point, the solution contains newly formed R2- and unreacted HR- until it reaches the second equivalence point. The solution contains only R2- at the second equivalence point. As titration proceeds after the second equivalence point, the solution contains R2- and unreacted OH- ions. You may understand by now why you have to stop the titration at the first equivalence point to incorporate only HL- ions into the reaction to determine heat of second neutralization of malonic acid. It is very important to stop the titration right at the first equivalence point. If you under-titrate the solution, you have more protons available than expected in the solution. It will cause greater temperature rise than expected. If you over-titrate the solution, you have fewer protons available than expected in the solution. It will cause less temperature rise than expected. A 120 milliliters of 0.250 molar malonic acid solution will be titrated with 2.5 molar NaOH solution. A pH indicator will not be used for the titration. Instead, a pH meter will be used to record the solution pH step by step as you add the NaOH solution drop by drop. As I said, it is critical to stop the titration right at the first equivalence point. Once you come this far, the rest of procedure is pretty straightforward. The remaining procedure is basically the same with the one that you did for HCl and NaOH. Start the Logo Pro on the computer. Open the cover and add 120 milliliters of 0.25 molar AH.n solution into the dual flask. Put the cover back and let the Logo Pro draw the baseline of the heating curve for 60 seconds. Keep agitating the apparatus to maintain thermal equilibrium inside the calorimeter. Pause the Logo Pro. Open the cover and add 12 milliliters of 2.5 molar NaOH solution into the dual flask. Put the cover back immediately. Continue the Logo Pro scanning for 300 seconds. Keep agitating the apparatus. Turn on the power of the power supply to initiate heating. Continue heating for another 300 seconds. Turn off the power of the power supply. Continue running the Logo Pro for another 300 seconds. Stop the Logo Pro and save the heating curve in text file for further data analysis. This is another generic copy of heating curve. There are two regions of temperature increase, delta T1 and delta T2. Delta T1 represents temperature increase due to an exothermic chemical reaction, a neutralization reaction of HR- and NaOH. It will be used to determine delta H2, that is, heat of neutralization of HR- and NaOH. Delta T2 is due to the intentional electrical heating, and it will be used to determine the heat capacity of calorimeter, Cp. Heat capacity may be different from the previous one, so you may have to determine it each time you use the calorimeter. The first step to determine Cp is to estimate the heat that was transferred electrically into the calorimeter during the intentional heating. The heat transferred Q equals I times V times T. I and V are current in amps and voltage in volts. That gives rise to 0.1 Celsius increase of 132 milliliters of water in every 10 to 15 seconds. T represents actual time spent during the intentional heating. It is approximately 300 seconds. Heat capacity Cp is defined by Q over delta T2. The unit of Cp is joules per Kelvin. Now you are ready to determine delta H2. Delta H2 equals negative Cp times delta T1. Since delta H's in the literature are reported in joules per mole or kilojoules per mole, you may want to convert delta H2 to molar delta H2 by dividing delta H2 by the number of moles of HR-. Like HCl, HR- is the limiting reactant in the reaction. Experimental value of molar delta H3 can be calculated simply by molar delta H2 minus molar delta H1. Now, let me tell you how to determine theoretically heat of ionization of water and heat of second ionization of malonic acid. Water is ionized into a proton and hydroxide ion. The heat associated with the reaction is negative delta H1. The theoretical heat of ionization of water can be calculated with the enthalpies of formation of water, proton, and hydroxide ion. You may find the values at the data section of your PCHEM textbook. The reaction enthalpy is simply the sum of formation enthalpies of products minus the sum of formation enthalpies of reactants. So, negative molar delta H1 is the formation enthalpy of proton plus the formation enthalpy of hydroxide ion minus the formation enthalpy of water. Determination of theoretical heat of second ionization of malonic acid is a little tricky, since the formation enthalpy of malonic acid is not available in the literature. You are not able to determine the theoretical heat of second ionization of malonic acid. Instead, you will use a similar weak diprotic acid, which is carbonic acid. The second ionization of malonic acid is written as HR minus ionizes into R2 minus and H plus. Likewise, the second ionization of carbonic acid is written as HCO3 minus ionizes into CO3 2 minus and H plus. The formation enthalpies of the reactants and products of the reaction can be found at the data section of your PCHEM textbook. The reaction enthalpy is simply the sum of formation enthalpies of products minus the sum of formation enthalpies of reactants. So, theoretical molar delta H3 is the formation enthalpy of CO3 2 minus plus the formation enthalpy of proton minus the formation enthalpy of HCO3 minus. You have determined experimental and theoretical heat of ionization of water and heat of second ionization of malonic acid. Now, I want you to include at least the following items in your lab report. Number 1. Include 2 heating curves, the one for the reaction of HCl and NaOH, and the other one for the reaction of HR minus and NaOH. Number 2. Compare the experimental heat of ionization of H2O with the theoretically calculated value. Describe what would have caused the discrepancy between the two values. Number 3. Compare the experimental heat of second ionization of malonic acid with the theoretically calculated value. Describe what would have caused the discrepancy between the two values. Please keep in mind that you should use the theoretical heat of the second ionization of carbonic acid to compare with the experimental value of heat of second ionization of malonic acid. Now, please log into D2L and take the online quiz titled Heats of Ionic Reactions.